Everybody good? And then, are we cool with ignoring this piece because it's just going to equal 0? All right, and I'm going to say that root 3, like I'm just going to distribute that 1 over root 3 to both of these, and I'm going to get root 3 squared over 3 minus 1. What are we finding it to be? 0. Before I decide, hey, something's wrong, what do you think we should do next? Because that feels weird to me to say that the average value of the function is 0. So the next thing I'm going to do is that we're going to graph this, and we're only going to graph it in between 0 and square root 3. What would you guys expect to see of this graph as we do this? I mean, essentially, okay. So what I'm seeing is I look at this and I'm looking at the graph. Certainly we have more negative values than we have positive values, but the positive values are more extreme. So if we were to take the average of every, I actually need it. This y value plus this one plus this one plus this one, they ended up they would balance each other out so that the average of those y values is 0. But we would definitely are not surprised to see some above the axis and some below the axis so that all those y values eventually cancel each other out. Okay? All right, let's try another one. The average value of 1 over x in between e and 2e. So that mean value will be 1 over 2e minus e times the integral. We doing all right? So 2e minus e is 1 over e. What is my integral of what is my integral of 1 over x? ln of x, evaluated from e to 2e. Okay? So I have 1 over e times ln of 2e minus ln of e. Thoughts? If I ask for an exact answer, what would you guys do next? Yeah. Are we comfortable with me saying ln of 2e, if we split that up, is ln 2 plus ln e? Because that multiplication can be split up into an addition problem. And where I find that useful is those cancel out, And I get ln of 2 over e is my final average value of the function. All right. Oh, wow. Okay. Before we move on. So, what the mean value theorem of integral says is not just that we can find the average value of the function, it also says that somewhere on the interval, there is a value c where f of c is equal to that average value. Okay? So, if I'm looking at this one, I want to find the value of c such that f of c equals that mean value. So in this case, f of c would be c squared minus 1, and we found that that average value was 0. So I want to find where does c squared minus 1 equal 0. So I get c squared equals 1, c equals plus or minus 1, except for we only care about the positive because our interval goes from 0 to square root 3. That's the value that's inside our interval. Okay? So sometimes I might ask you to find the average value. Sometimes I might find the x value. I might ask you to find the x coordinate guaranteed by the mean value theorem of integrals. Okay? If I asked you to find the x coordinate guaranteed by the mean value of integrals here, I would say, well, what is g of c such that, again, that mean value? So in this case, that would be 1 over c equals ln 2 over e. And you guys, we can just reciprocate both of those to solve that. Everybody good? So that would mean c would be e over ln 2. Feels like exact answers are a reasonable expectation. Cool? All right. All right, you guys. So, these next few examples are designed to make the next theorem that we have, the second fundamental theorem of calculus, make some sense. Okay? So, g of x is going to be a function that is the result of integrating this right-hand side of the equal sign. Okay? So, we're integrating with respect to t, but when I do that, you guys, by the way, what is the integral of cosine t? Sine of t. And if I'm integrating that from 1 to x, so even though my original kind of expression, I'm integrating with respect to t, because my bounds have an x in it, the result is going to be a function of x. So, I was given, this doesn't look like it is a function of x when you look at it in its original form, okay? But the fact of the matter is, no matter what variable I have here for cosine t dt, it could be cosine y dy, it could be cosine delta d delta, though that would be a really weird one, okay? It could be cosine snowman d snowman. The minute my bounds have an x, once I do that integral, I end up with a function of x. Is everybody with me so far? Okay? Now, I'm asking you to take the derivative of this function. What is the derivative of g now that we have this? Well, the derivative of sine x is cosine x. What's the derivative of sine 1? 0. Because what do I know about the sine of 1? It is a constant. Everybody good so far? And likewise, let's look at this one next. I'm integrating with respect to t. But once I do that, I now have a new function that is with respect to x. Everybody good? And if I asked you guys, what is the derivative of this new function? It would just be cosine of x. The derivative of sine x is cosine x. The derivative of sine of 3 is 0. Okay, so the first thing is, as we look at just those two problems, we essentially, whether there was a 1 here or a 3 here, I could put any number I want here as long as the part of my expression is a constant. Once I take the derivative of that piece, I'm taking the derivative of a constant. It's going to go away. Is everybody with me so far? All right. Go. Let's look at this one. This one's going to look a little bit different. How is this different than the previous two examples? Now when I go to take my derivative, I have an inside function. Technically I did up here too, it's just that inside function was x. Now it's x squared. And if I asked you to take the derivative of this expression, what's the derivative of sine of x squared? It's the cosine of x squared times 2x, because you would have to chain rule it. Is everybody, does this make sense? Okay. What about the sine 6? What's that derivative? 0. Okay. So if my bound is a function, I have to consider that when I take my derivative. Okay? So in some respects, like up here, it's almost like I'm gonna, when I integrate this and then take the derivative, I'm gonna end up right back where I started, except for now I have an x in that spot, so I have to multiply by the derivative of whatever that bound is. Okay? So using that set of rules, it's almost like I can jump right away to saying the derivative of this integral is going to be the cosine of the square root of x. And what I've got to remember is I also then have to use the chain rule and take the derivative of that square root of x. Which is 1 over 2 root x. So the integral and the derivative are kind of canceling each other out, but we got to remember that if my bound is a more complex function, I have to use the chain rule to multiply by that function. Okay? So how might I ask you about this? I might say take the derivative of the integral from 4 to 3x of sine of t. Everybody good? If I integrate and then take the derivative, I'm going to go back to, if I integrate it, it would become negative cosine. And then I take that derivative, it comes back to sine. My inside is 3x. But if I were to take the derivative of that, I would have a 3 out front. Because chain rule says I got to take the derivative of the inside as well. Everybody okay? So, what would this one be? To start, I don't know how to integrate the square root of 1 plus secant. I'm sure that would be a pretty challenging one to do, okay? However, I'm not just integrating it. After I take the integral, I'm going to take the derivative. So the derivative and the integral part would cancel each other out, and we put in that new function for x. So I also then, now I took the derivative with an inner of 5x squared. So I need to take the derivative of the, multiply the derivative of the outer. The derivative of the outer is just doing that replacement, times 10x. And that is